What's up, everybody? Now we are going to talk about Lyapunov function computation, but to prove, not for the wait a sec. In the previous video we talked about global subit, right? Okay, we computed some Lyapunov function v, and we basically impose these 5 constraints, right? Okay, but this was for global case, meaning whenever you start, your trajectories converge to origin. Okay, but now we are look at local case. Okay, and how would you like express your express your constraints on your Lyapunov function for local case? Okay, local asymptotical stability case. Okay, and here's the constraints. As you can see, only this part change. Let's look at this again, right? This is basically for all x in Rn. Basically says that, and but it says only you need to find the Lyapunov function such that these constraints are satisfied only in a given. It can be a ball, it can be elliptical region, right? And only in a neighborhood, specific neighborhood of that origin or equivalent point. Okay, but it probably will be origin. Okay, and okay, how would you express this problem, and how would you put this in a SOS programming framework that we have talked about this in the previous video, right? In the previous video I just published, by the way, in 1 hour ago or something. Okay, all right, let's do some little manipulation. Okay, here, let me get my pencil. All right, okay, all right, and if you recall the polynomial optimization using source programming YouTube video, right? I just published like 2 hours ago or something, and we basically talk about that. How would you, we have some constraint optimization problem. How would you turn a constraint optimization problem to unconstrained optimization problem? Basically, you would use Lagrange multipliers, right? However, since this is like polynomial that we are dealing with, and there is a polynomial, I guess, equivalent of Lagrange multipliers and or the theorem, and it is called positive Sterling-Satz. Okay, and I guess it's German or something, right? And I talk about that subject in the video, right? Like polynomial optimization video. The title of the video is polynomial optimization using source programming. Okay, you can check that out. Okay, and so now I am going to do some manipulation, and it will make sense if you watch that video. Okay, or if you're familiar with that subject, I guess. Okay, here those two constraints, they are changed. Okay, and now we need to find, maybe I should, yeah, it can, I mean, it's not wrong. Okay, local asymptotical stability. Okay, and for a given dynamical system, find a v of x such that these 6 constraints are satisfied. Okay, where we just introduced 2 SOS polynomials. Okay, and we have 1, 2, 3, 4 SOS constraints now. Okay, all right, so let's go back to MATLAB. Okay, and let me change my screen. Okay, here this is SOS Lyapunov local 001.m. You can download that MATLAB script. Okay, and First of all, before doing anything else, let's go at the end of this script and let's run it. Let's run this script. Okay, and you don't see that much, but all the trajectories converge to 0. And why you would use local asymptotic and not the global asymptotic? Or why would you not think that this system is not or is global asymptotic stable? Well, first of all, let me say something. This is, if you're like a dynamics geek, this is what you call, yeah, Van der Pol oscillator. Okay, oscillator. All right, and so what I'm going to do now is this. I'm just going to delete these minus terms. By doing that, I just reverse the dynamics. Okay, it's like, and now let's check the trajectories. Again, the trajectories start really close to origin. Okay, let's see where they go now. Okay, we just reverse the trajectories. Okay, and wait a sec, I made a mistake. Okay, here is the trajectories. We can see that, and it's a really beautiful picture, right? Okay, and I think I should put this in thumbnail, I guess. Okay, anyway, and so if you start from this location, you would diverge, right? But if you reverse the dynamics anywhere in that region, and it's also called region of attraction, right? And anywhere if you reverse the dynamics for Van der Pol oscillator, anywhere in this, let's call it black square, right? Let's call it middle square, and you would converge to origin. Okay, but and if you are here, you would diverge. Okay, because this is, let's call it stable Van der Pol oscillator. Okay, and if you reverse the trajectories, let's name that system unstable Van der Pol oscillator. Okay, and if you, for unstable Van der Pol oscillator, if you start here, you will diverge to infinity, I guess, right? Okay. Okay, so, and local asymptotical stability and finding Lyapunov functions to prove that, what I'm trying to say is that it can also be helpful to prove the existence of limit cycles, right? Is also another subject for dynamical systems. All right, so let's close that and let's, yeah, look at our script. Okay, and here, this is, let's call it unstable Van der Pol oscillator dynamical system. Okay, this is the dynamics of unstable Van der Pol oscillator. Okay, again, we just, wait, let me show you. Wait, it's like 65, 35. It's like 30 lines of code. Okay, again, nothing to worry about. First, we again initiate. By the way, you are able to see that, right? Okay, let me just make it bigger, at least. Okay. Okay. Right, let me calm down a bit. All right. I am looking at the screen and I hope you're able to see that. Anyway, if you're not able to see that, I mean, you should be right now. Okay, you can download this code, right, from the GitHub page, link given in the description down below. Okay, and please leave a like. By the way, it would help. And okay, these are the dynamics. These are the indeterminates. And okay, this is the degree where we maximum, I guess this is the degree, and we are basically saying, hey, we know that we have some inside information about our Lyapunov function. We think our Lyapunov function will be fourth or less order, right? Okay, we could easily change that and say 6 or 8 or something, right? Okay, All right, and again epsilon 1 polynomial, right? Okay, we have talked about that, and let me go back to the board and show you. Yeah, yeah, I kind of, I mean, I don't want to say a mistake, but yeah, I should also write something like this. Just give me some time. Okay, not gonna take long. Wait a sec. Okay, minus epsilon 1 x square. This should be SOS. Okay, and also let's do the same for that. You are able to see the screen, right? Okay, SOS in minus epsilon 1 norm squared. Okay, all right, so epsilon 1 polynomial I just named in the script is this basically. Okay, all right, epsilon 1 polynomial. Let's change the screen. Let's go back to MATLAB. Okay, we are recording, right? Okay, yeah, this is epsilon 1 polynomial. Okay, and here we are initiating our defining our Lyapunov function, and for each decision polynomial there is corresponding coefficient vector and monomial vector. Okay, right, and again we have talked about sigma 1 and sigma 2. Let me SOS functions. Let me change the screen. Here sigma 1 and sigma 2, and they need to be SOS. Okay, SOS polynomials. All right, let's go back to MATLAB again. All right, again we define them as being like fourth order polynomials. Okay, and we need to define minus v dot expression. Okay, and here we are defining that we are going to use MOSEC or STP3 as our STP solver. All right, and these are again our constraints for group. Yeah, I mean we talk about our constraints, right? Okay, this is our constraint objects, right? We are going to stack our constraints on top of each other and then supply that to our optimization tool. Okay, and here we are just, I mean, this is this constraint and this is this constraint, and again we have talked about this constraint in the previous video. Okay, check the global asymptotical stability using TOS programming. Check that my YouTube video, right? And again we are limiting the degrees of freedom. Yeah, this is just to limit the degrees of freedom. Okay, because anywhere any Lyapunov function that is valid, I mean by multiplying with some type of scalar number, we can make this equality hold. Okay, all right, again we want our coefficients lie between 0 and 100. Okay, maybe 10 by the way, you can just do that, and if it doesn't work you can go up to 100. Okay, all right, and this is our first constraint, right? Let's keep that, by the way, R is this. Okay, R is this, and let's keep this, okay, in mind, and let's go back to tablets. Okay, here basically that long line indicates this constraint. Okay, again change the screen here. All right, and that long line indicates, let's back to indicates, let me get my pencil, this. Okay, all right, let's change the screen. Okay, and we recall those sigma 1 and sigma 2 being SOS. Okay, here, two SOS constraints. Okay. And finally, here, solve source command. Okay. These are the constraints. This is a feasibility problem. We don't have any objective to minimize. Okay. And options. Okay. We just indicated our STP solver in that options object. And what are the, I guess, numbers that we need to find? These are coefficients of the Lyapunov function, okay, or let's call it polynomial, right? And also coefficients of the sigma 1 polynomial here, right? Here, and coefficients of the sigma 2 polynomial, okay? All right. Because YOLMIP needs to know, hey, which, for example, this is STP var, and let me go up. Yeah, and this is STP var too, right? I mean, which term is indeterminate and which term is some number that we need to, or I need to, right? I am YOLMIP in that analogy. I need to compute. Okay, and let's run it. So let's run it. Okay, it says successfully solved. All right, and this, like, how many? Yeah, 15 lines of code. You can just check it on your own time, right? Because I kind of talk about that. It is, we computed the Lyapunov function, okay, here in this section, okay, and we just need to, hey, write this down, our Lyapunov function, would you? Okay, and let's run it, and then write it as and define it as a symbolic object. Okay, here, by the way, the name, these are my videos. Okay, and this is here as v of Lyapunov polynomial as symbolic object, and it is incredibly long expression. Okay, all right, and finally output the v and minus v dot expressions. Okay, let's run this section, and let's run this section again, maybe. Okay, this is here, this is, yeah, VPA is just to, hey, just give me 3 digits after the, you know, points. And all right, so this is our Lyapunov function, and this is the end of the story. Okay, and again, you can, and you should check the trajectories. Okay, all right, and that's all. Again, you can download this script and also documentation from the GitHub page, link given in the description below. Okay, and please leave a like, and that's it. Thanks for watching.